I grew up in the 90s where computers looked like this and the internet sounded like this. Amongst all the games that were handed around on copied CDs, one of my personal favourites was RollerCoaster Tycoon. I spent hours designing rides, perfecting parks, and occasionally doing something cursed. There's a bit of a legend around RollerCoaster Tycoon in that it was developed by one guy entirely in x86 assembly. No C, no C++, nothing high level. I thought it would be fun to spend a bit of time reverse engineering the original RollerCoaster Tycoon to see what we can learn. Don't worry if you've never done any reverse engineering before or even looked at any assembly. I'm going to explain what I do as I go along, the tools I use, and my thought process. There's three main tools I'm going to use for this: Ghidra, an open source disassembler and decompiler from a small American government agency; x64 Debug, an open source Windows debugger; and Obsidian, a free note-taking app. I cannot stress the importance of taking notes as you do reverse engineering, as there's normally so much going on you cannot keep it all in your head in one go. Before we dive headfirst into the code, there's two things I like to do when reverse engineering. 1. Set a goal. It's so important to have a goal in mind when you do reverse engineering, as it's so easy to get lost and fall down rabbit holes. For this video, I want to see how does RollerCoaster Tycoon do its rendering. 2. Do some initial research. It's useful to get the lay of the land and potentially get some threads that you can pull on when you get stuck. From a quick search, I found the original author's website, which is straight out of the 90s, and in the FAQ he mentions DirectX 5, so that's something that we want to explore. Further to that, I looked up some DirectX 5 tutorials from other relics of the old internet. I mean, look, this site is amazing. I wish more sites looked like this. So I'm pretty much an expert on DirectX 5 now. If you don't know DirectX, don't worry, it's just a graphics API like OpenGL or Vulkan provided by Microsoft. As an aside, reverse engineering tools seem determined to make text as small and as hard to read as possible. So where possible, I have embiggened it so that it's easier to read, especially on mobile phones. So the first thing I'm going to do is open up the binary Ghidra. This will provide us with an initial disassembly of the program. So I'm going to click yes, I want to analyze it. This is going to churn through the binary and give us all the functions inside it and all the assembly for it. So that's happened pretty quick, which is good. So then first thing I like to do is look at the imports. So interestingly, I can see here that it's importing some DirectX DLLs, but maybe not all of them. I would expect there to be like ddraw for the 2D drawing, but that's fine, we'll have a look later. And inside functions, so this is interesting. Not a lot of functions in this binary. I expect for a game there to be lots and lots of functions. I can see here that it comes into entry, and the first thing it does is just jump to another function, which then calls another function, and then does some stuff. Of course, load library, gets proc address, so this presumably is doing like some sort of initial setup. It's going to load some extra libraries in, some extra DLLs, which maybe is why we couldn't find direct draw. So after an initial glance, I've not really gleaned too much from this. I can see it's calling load library, and then trying to find some functions in it, but again, not entirely sure what's going on. So normally what I do now is look at all the strings in the binary. All your strings get embedded in the binary somewhere to be loaded, and we can Ghidra will find all those and put them in a list for us. So here are all the strings in the binary, and there's really not a lot for a game. For a reasonable sized executable, I'd expect there to be much more. There's a list of the libraries that it's imported. There's the functions that it's called. So I can see co-create instance, regkey create, a few others. Some random strings with ASCII characters in. That's kind of it. There's nothing in there. So if we run the game, we can see, for instance, even on the front page, there's like tooltips. So start new game, load save game, show tutorial, exit. I would expect, unless those were all images that have been pre-rendered, I would expect all those to be strings within the binary, and then at runtime the game will create those graphics. That's what I expect, so I'm very surprised there's very few strings in here. So I think what we need to do is move on from the static analysis to the dynamic analysis. So static analysis is just looking at the disassembly, looking at what's inside the binary and trying to figure out what's going on from there. What I actually want to do is now run it under a debugger so I can pause it and kind of see what the program actually does at runtime. So that'll fire up x64 debug, or technically x32 debug, because RollerCoaster Tycoon is technically a 32-bit binary. So what I'll do is I'll open up the binary, and this and the debugger will instantly launch it but pause it right at the beginning. So what I'm interested in doing is going to this entry function that we found in Ghidra and then just kind of seeing where we go from there. So first thing I'm going to do is I'm going to go to the entry address that we found in Ghidra. So I can jump to that. Then just put a breakpoint on this. So as we can see here, so if I just start the application again and go through all this Windows setup chuff, we end up here at the entry point. So this jumps into whatever this instruction is. So I can jump here, jumps into this method where it starts doing all the load libraries and finding addresses. So had a little look around and not really found anything interesting yet. But what is interesting is if we run it as normal, so we'll just load up a game, Forest Frontiers, Classic, and then we pause the program. So if we look at the call stack, which is just the list of functions leading up to wherever we paused it, we can see here that we're in this function here at this address. But if we take this address and copy it, and then go over to Ghidra and put that in, there's nothing there. So, which is very strange. So in the standard binary, when you execute it, there's no code there, but when you run it, there's code there. So this can mean one of two things. Either the code itself is obfuscated and it's unpacking and deobfuscating when you run it, or it's loading in the code at runtime. So it's finding the code somewhere else and bringing it into the application. So what I'm going to do is I'm going to restart this and look at the memory at that address, and it's all zeros. So this suggests to me that the program code is actually being loaded in at runtime. If it was being obfuscated, i.e. the developer was deliberately trying to make reverse engineers' life difficult by having the code in there but in a form that's impossible to read in a debugger, then I would expect there to be like random looking data in here, which would be deobfuscated at runtime. But as it's just zeros, and you can't really apply the algorithm to zeros to give you meaningful data, I think that's probably loaded at runtime. So what I've done is I've set a hardware breakpoint on that block of zeros. So a hardware breakpoint means we can break as soon as something reads or writes to that address. So what this means is that we can rerun the program, and as soon as something writes to it, the debugger will stop and tell us. So rerunning that now, we can keep going until we get a hardware breakpoint. Go on rep mods D. So this is a repeat move instruction, which is normally used in like a mem copy. So this suggests that we are now mem copying data into that region of zeros. So just having a quick look up before we set up this loop, we call this function, and this function does a whole load of load libraries and get addresses. So let's just set a breakpoint at the start of this and rerun it. So here we are at that first load library call in that function that we saw. The library it's learning is kernel 32, so that's just a core Windows library. From that, if we step through it, it's starting to load functions like get module handle A, get module file name A, global alloc, create file A, create file mapping. All these functions suggest that we are opening up a file, mapping parts of it into memory, and then afterwards we're going to be using that memcopy primitive to move them into the right place. So this is effectively loading the code in. I'm not too fussed about this. It is interesting, but seeing as our goal was to find out how the code does its rendering, this is really kind of just a rabbit hole that we're falling down. So I'm kind of happy to assume that this works, that this loads the code in, and then we can just continue from there. So the problem we've got now is that Ghidra, one of our tools, only sees the bootstrapping code and can't see all the stuff that's loaded at runtime. However, there is a trick we can use to get that. So if we just run the game as normal, now it's all been loaded into memory and all the code is actually there in the process. So if we open up Task Manager, we find our running application, right-click it and go Create Memory Dump File. This will then dump all the memory that's currently being loaded in to a file. So then we can go back to Ghidra and open that dump, and that will have all the code that was running at runtime. So something strange has happened here. I've asked Ghidra to do its analysis, which will find all the functions and the strings and do all the processing so that we can kind of start to dig into it. And it's been running for quite some time, like I think about an hour now, which is way longer than anything should take of this size. So I don't know if it's because the binary has been written in assembly and not been compiled, that it's gotten Ghidra confused, or maybe it's just because I've dumped the running process. But either way, I've had to just stop the analysis, which means Ghidra's not going to be super helpful going forward now. But I believe but I believe it has actually now found all the strings, which is super useful. Yeah, look at that. So it's loading loads and loads of strings now. Yeah, that's a lot of strings. But let's search for something that we know we've seen in the game. So that's start new game tooltip. We found that string as it exists in the binary. However, again, something else strange here is that I would expect there to be a reference to it. So what Ghidra does is once it finds a string, it will then also find the code that loads that string. So what I'd expect to find is a function somewhere which loads the string start new game, and that function might be like the menu handler or a tooltip generator or something along those lines, and then that kind of gives us a thread to pull on, so we can kind of start there and then work our way up into this menu code and then maybe find some rendering code. However, Ghidra's not found anything that references this the address of this string. Now it could be because of the analysis, or it could be because something strange is going on. So to dig into this, what we're going to do is we're going to take this address, go back over to our debugger, remove all the breakpoints that we've got so far, start again, and then go to this address. So again, this is now for the zeros because the debugger has paused the program as soon as it starts, which means it hasn't loaded in the binary, hasn't loaded in any of the code yet. So what we can do is we can set a hardware breakpoint on this for access. So this means as soon as someone reads from that address, it will stop. So what I'm hoping is at some point, some code is going to want to read that start new game string, and then we can kind of see where we are from there. So continue. So the game is now running as we expected. We're in the menu, hover over that, and it breaks. Okay, so when it went to render that tooltip, it actually tried to load that string into memory. So this is good. This means that we found the code which loads that string. So what I'm going to do now is put a look around, just see if we can find anything useful around here. So interesting. What it's done here is to get the address of the string, it's taken EAX in, times it by 4, then added an offset. So that offset, A8220C, is kind of in the region of all those strings. So what this suggests to me is that this is some sort of lookup function. So A8A220C might be the start of all the strings, and then EAX is the offset into that. So let's just have a little look up, see if we can see anything else. So something interesting here. Before we do this offset into what I think might be where all the strings live, there's a comp instruction with AX. So the first part of AX against 8000, and only if your register is above the value 8000 does it then go to this code to then times it by 4 and add it. But interesting, on the red path, so this is if it's below 8000 it goes this way, if it's above 8000 it goes this way, and then does the same with 9000, and then the same with E1000, E0000. So what I think this function is, looking at it, is some sort of like decoder for values. So you give it an ID, and if that ID is less than 8000, then it's a string, so it looks it up. If it's less than 9000, it does something else, and then if it's less than E1000, it then does something else. So I wonder if, rather than anything referencing the strings directly like you would have in normal code, I wonder if what the developer has done is just put all the strings in one massive array, and then just given each of those effectively an ID, and then when you want that string, you call this function with the ID, and then that returns, that goes and finds the string for you at that offset and loads it, and then you can kind of use other larger values to represent other data. Again, not going to spend too much time going through this because I think it's diminishing returns for what we want to do, which is find the rendering code. But again, kind of interesting to see how this works. There's definitely this, like, if less than 8000, if less than 9000, if less than E1000 logic going on here. It definitely loads a string using this, this formula here. So taking a step back and looking back at the original research I did and the notes I took, I know that we're using DirectX, and all the DirectX tutorials I read suggest that all the code really has to start with this call to this function called DirectDrawCreate. It says here this creates an instance of a DirectDraw object. So this will return you an object which conforms to the DirectDraw interface, and that interface has all these functions including create palette, create surface, enum surface, get display mode, blah 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 blah, a whole load of stuff. So this function really is the first one we need to call in order to get started with DirectX. Now, under the hood, this is all COM, the component object model, which is Microsoft's IPC mechanism, but I'm not going to get into the weeds of that. I'll just pick out bits that are relevant for this. So, direct draw create. So if we go back over to x64 debug, or x32 debug in this case, I've got this just paused as the game is running, and we can see here a list of all the modules that it's loaded. So all these libraries have been loaded at some point during the program, and I know that ddrawdl is the library with all the direct draw code in it. So looking at the exports, so these are the functions that you can call within the library. There's not actually that many, but it does include direct draw create and direct draw create ex. Classic Windows 32 here. Windows is super committed to backwards compatibility, so it really doesn't like changing any of its API functions. So what you find is at some point Microsoft has decided that a function needs more arguments, and rather than breaking backwards compatibility and adding those to an existing function, it will just create a new one and add ex on the end for extended. You'll see this all over the Win32 API. I don't know which of these is going to be called in the program, so what I'll do is I'll set a breakpoint on both, and then I will restart it. Go through all the beginning Windows chuff again, and see if we... Right, here we go. We've stopped on direct draw create. So I know that direct draw create is called at some point in this program before it starts. So looking at the taskbar at the bottom, the GUI component of this executable hasn't started yet. So we are calling direct draw create. So this kind of suggests we're going down the DirectX route. Looking at the arguments for direct draw create, you give it some GUID that represents a driver to be created, however it can be null, so we can skip past that. You then give it a pointer to a variable to be set to a valid iDirectDraw interface. So this is the COM part here. So COM really works in terms of interfaces. You define a struct which has a load of function pointers in it. That is your interface. And then when you create one of those COM objects, some internal library code will make sure they're all set to the right, all those function pointers are set to the right place, and it will just return you this interface. So let's actually have a look at this in code. So here I've got one of these tutorials, and it says here, the DirectDraw or DirectDrawX function call can be used to create a DirectDraw object. And you can see in this example here, it's null, the first and last argument are null, so we're not too worried, but it passes in here the address of a gpdd variable. If I go find where they've defined that, so here we can see, look, the DirectDraw object is called gpdd, and it is, the type is an LP DirectDraw. So one, I always find Windows programming hilarious because they define so much stuff in uppercase, and it always just sounds really angry. Like, why are they shouting that the type to me is LP DirectDraw? But that as an aside, Win32 code often embeds the type into the variable name, for better or for worse. So LP here means pointer to a DirectDraw. So this type here is actually a pointer, and what you've done here is passed in the address of that pointer. So if this all sounds really complicated, I wouldn't worry too much about it. Basically, what you're doing when you call DirectDraw create is passing it the address of 4 bytes where it can stamp in the address of the thing you want to use. So you're basically saying, I need a pointer to a DirectDraw object. Here is some space where you can tell me what that pointer is. That's really all it's doing. So let's see if we can see that in action first. So we're paused on DirectDraw create and looking at the stack arguments. So because this is a 32-bit process, the arguments to a function are passed in on the stack, and it is the Windows calling conventions. Arguments are passed right to left. So the bottom one will be the third argument, and the middle one, then the second one up will be the middle argument, and the top one will be the first argument. We can see here that the second argument is an address. So if we follow this in the dump, we can see here that it's basically called DirectDraw with pointer to some memory that's all been zeroed out. So what I'm going to do is, so what I expect is after this call is finished, these 4 bytes will point to the DirectDraw object. So what we can do now is just look at the call stack and find out where we actually called this from our user code. So we can see we called this function here, which will be the DirectDraw create, and then we continue afterwards. So what I'm going to do is I'm going to set a breakpoint here in the game's code after it makes this call to DirectDraw. If I just continue, right, we're here. So basically what's happened now is we've called DirectDraw create, and then we've paused straight after it. And looking back at the memory, we can now see that there is indeed a 4-byte address stamped into this memory. So again, what we've asked it to do is we said, here is 4 bytes, please write into it the address of the DirectDraw object. So what I can do now is I can now follow this in a second dump. So this is now all the data hanging off that pointer. Now, to be super confusing, com objects point to a pointer to the array of function pointers. This is much like vtables in C++, but don't worry if that doesn't make any sense. Basically, what they've given me is a pointer to all the function addresses. So if we now follow this in another window, so we can see here lots and lots of addresses, and the debugger has told us that these are all in system data, so these all exist in loaded in libraries. So these are pointers to Windows code, which is kind of what we expect, because we've gone to DirectX, which is a system library, and we've asked it for a pointer to a pointer to a pointer to a bunch of other functions that we can call. So let's try and bring this all back to something real. DirectX 5, as you might expect, is not particularly well documented on Windows anymore because it is quite old. So what I've found through some Googling is an archive of the old DirectDraw header file that you would have been given back in the day if you were coding in DirectX 5. So what you get here is the common definition of the iDirectDraw object. Again, it all looks grim, and it's Windows programming, so it is a little bit grim, but basically what you can see here is that you declare this iDirectDraw interface, and then these are all the methods that are part of DirectDraw. So what you're basically saying here is that when someone asks for this DirectDraw object, here are all the functions that they can call off of it. So you've got the standard 3, which are from IUnknown, which is the base object for all the COM objects, and then you've got all these here. So actually looking at the modern documentation for iDirectDraw, if we look at the overview, we can see that it should have functions called compact, create clipper, create palette, create service, blah, 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 and these all exist in this structure definition. So there are 23 functions in here. And if we look back over our memory, there are 23 functions and then a null byte. Now, I'm not a COM expert. I don't know if all those function arrays are terminated with a null byte, but this kind of suggests we're in the right place. So going back to all our DirectX 5 tutorials, the first thing you do after creating a device is you want to call create surface. So surface is the thing you're actually going to render to. So this is 7 functions in. So going 7 functions into our memory, 5, 6, 7. If I now open this up in the disassembler, this should be the function for create surface. And in fact, x64 debug has filled in some additional metadata here, and it looks very much like this is the function for create surface. So what we've done is we found where DirectDraw create was called in the code. We know that that returns a pointer to a pointer to a pointer to a bunch of function pointers. And then we know from the documentation that the 7th function pointer is to this thing called create surface, which we know should be called as part of the regular DirectX setup, or DirectX 5 setup. So what I'm going to do now is set a breakpoint here, and then rerun the program again, and hopefully we should hit this. Hi. That's not what I expected. Didn't call it. Let me just try again. So DirectDraw create, and at some point, okay. Something strange is going on here. We've found the DirectDraw create function, we've looked at the return object, we found the function in there that we expect to be called on it, and yet it's not being called. Okay, I'm gonna have to a little dig around now, I think. Okay, so I've gone through all these function pointers and I put breakpoints at the beginning of all of them and then restarted it, and the only one that seems to actually be called is this enum display modes. So this enumerates all the display modes that the hardware exposes through the DirectDraw object and that are compatible with a provided surface description. Doesn't mean a whole lot to me, but let's have a little bit of a dig to see if we can glean anything useful from it. So I've read the docs, and this is basically a reasonably standard enumeration method in that you give it a callback, so a function, and then it will call that function for you every time it loops through whatever it's enumerating through, in this case, display modes. Okay, so what I've done is I've restarted it, and then I put a breakpoint on the point where this where this enum display modes function is called. So the arguments to this are, let's look, it's expecting 4 parameters, but because it's COM and because it mimics C++ vtables, there's actually an implicit fifth argument, which comes first, which is a pointer to the COM object. So in C++, it's the this keyword. So we should expect 5 arguments, and those would be the pointer, the object we're calling it on, which is that, and then it's giving it 4 nulls. So these are all 0, whatever those are, and then the last one is this LPD nummode callback, an address of the enummode's callback function. Right, so this here is the function that we have, the game is asking the Windows code to call every time it enumerates one of these devices. So we can just go to this, put it into assembler. Oh, it's just up here, and looking at this just loads an address into EAX, adds 1 to it, and then stores it back into the same address. Oh, so this is just counting it, right? So all this is doing is counting the number of devices that it finds. So that's not particularly interesting or useful to us at the moment. Okay, so I've not really gotten anywhere yet. So what I'm going to do is take a step back. We know that our goal is to find the rendering code. So what I'm going to do is remove all my breakpoints and then restart the game. We get to the point where it's actually running. Okay, so here we are. Game is running. Start new game, Forest Frontiers. And then I'm going to pause it. So now it's paused. I don't actually know what pause does in the game, but I'm going to assume that it means that the physics and the AI and kind of a lot of the subsystems are no longer running, and all it's really doing is just rendering the current frame. What this means now is that I can go to the debugger and suspend it and just see where the call stack is, and statistically, if I keep doing that over and over again, I should, in theory, end up somewhere in the rendering code, because the rendering code really should dominate the program at this point. Like I said, it's not really doing anything else other than just rendering the scene. So I'm going to keep doing that a few times and just see if I can kind of get an idea of where we are. Okay, so I've been running and pausing, and I've eventually found myself in this function. Again, I haven't looked at it too much, but I have noticed that right at the end of the function, there's this call to GDI flush. So looking at the docs for this, the GDI flush function flushes the calling thread's current batch. So basically what this looks like it does is you issue a load of draw calls, and then when you're done, you call GDI flush, and then that executes them all at once. This is really interesting because GDI is a software renderer part of Windows. And by software, I mean it runs entirely on the CPU. It doesn't use your graphics card at all. In fact, one of the reasons they created DirectX was to enable hardware acceleration for game devs. It was to provide access to the graphics card. It seems a bit strange that everything I've read says RollerCoaster Tycoon uses DirectX, but it seems to be using GDI for the actual rendering. Maybe it's using DirectX for sound or input or some of the other parts of the DirectX API. So what I then did was just keep walking through the end of the function. I ended up in this loop. So this is quite interesting. Calls up a whole bunch of functions, of which one of them calls GDI flush and then jumps back to the beginning. So I think this might be the game loop, because it calls into this GDI flush function, then goes back to the top and then does another stuff, then calls back into it again. If we have a look into one of these other functions, we can see that it calls peak message A, translate message, dispatch message. This is classic Win32 event loop handling code. So I think this might be the event, the main game loop. Does some rendering, then it handles all the window messages. Does some rendering, then it handles all the Windows messages. So I think we're on the right track now. So it looks like I might actually be using GDI to do the actual rendering rather than DirectX. So I've set some breakpoints on some of the other GDI functions just to see what's being called, and it seems like this stretch DI bit is called pretty frequently. So stretch DI dirty. So this function copies the color data for a rectangle of pixels in a dib JPEG or PNG image to the specified destination rectangle. The destination is specified by device context. So this kind of suggests that this function is being used to copy an array of pixel data into a device context, which probably means a window. So I think this is being used to copy data to the actual window that you see. In fact, I can see here it calls stretch DI bits, then it calls GDI flush, then it calls stretch DI bits, and then it calls GDI flush. So there's one stretch DI bits function called before GDI flush. So again, this kind of suggests that it's using this function to copy all the data over to the window, and it's flushing all those, and it's flushing that draw command. So if we look at the arguments to stretch DI bits, we can see here it takes quite a lot, and one of those is LP bit, and that is a pointer to the image bits which are stored as an array of bytes. So if we look on the stack for the 10th argument, that is this address, and if we look at that in the dump, that potentially could be a bunch of RGB triplets. So RGB byte, RGB byte, RGB byte. Also supplied with this is a I usage, which specifies whether the colors member of the info struct, which we'll look at in a minute, it contains explicit red, green, and blue values or indexes. So bitmaps are quite complex. They either contain RGB triplets or they contain a series of indexes into like a lookup table of colors. So I'm kind of hoping that it's just RGB triplets because it's much easier to decode and have a look at. So see if we can find what this value is. And 00 is RGB colors. So I'm kind of hoping that the next argument, this I usage argument, is 0. So that would be 1, 2, 3, 4, 6, 12, and the 12 is 0. Okay, so fingers crossed, hopefully on the right path. So the previous argument to that is a bitmap info struct, or a pointer to a bitmap info struct, and this defines the structure, defines the dimensions and color information for a div, which is the bitmap. So, and again, I'm not an expert on Windows bitmap formats. I'm just kind of figuring a lot of this out as we go along. So this struct has a header and then an array of colors. So this header contains a whole host of information about size, width, height, planes, bit count, compression, etc., etc. So let's dereference that. So let's put that in the dump. So the first argument is the size, so 28 bytes. I'm not going to check that, but that could very well be 28 bytes. Then a width, so 500. So what's so 1280 by, and then height. And this seems quite a large number. FC00. Looks like a minus number. So height specifies the height of the bitmap in pixels. For an uncompressed RGB bitmaps, if height is positive, the bitmap is a bottom-up div with origin at the lower left. If it is negative, the bitmap is a top-down div with the origin at the upper left. So this could be negative. It just means that the origin is flipped. So if we negate this, okay, so 1024. Okay, so possible dimensions we've got there. Those all seem sane. Planes, not too familiar what planes are in terms of bitmaps, but this value must be 1, and it is indeed 1 because this is a word which is 16 bits on Windows. We've got the bit count, so this specifies the number of bits per pixel, and that is 8, which is what we're hoping for, 8 bits per byte, which would give you 8 bits per RGB component. Compression is 0, so I'm going to assume that means there is no compression. And specifies the size and bytes of the image. So that is 14,000 divided by 3 bytes per color divided by 500. Numbers don't quite add up there, but again, I'm not an expert on bitmaps. Maybe there's some extra calculations that go into the size. But this all kind of seems roughly what we expect. So what I'm going to do is, okay, so I've taken those bytes, I've dumped them into a file. Now, there is a file format called PPM, which is a very simple image format, which consists of a header saying how to interpret the data, and then the dimensions, and then maximum value of any byte. So I've already had a little play around with this, and I think this is roughly right based on the numbers that I sort of went back and double checked and had a look at. So P6 means expect all the values in RGB triplets of 1 byte each, and then 640 by 480 image size, which I think might be the size of that render window we've seen, and then the maximum value 255. So what I've then done is used image magic to convert that to a ping. So this is a super simple way of generating pings by just dumping raw RGB triplets into a file. And then if I actually go and find this and then open it up, not quite what I was expecting, but like I can clearly see here the level, right? There's the entrance gate, there's the path, there's the trees, that's the HUD. I've obviously just gotten some of the values wrong or interpreted them slightly wrong, but I think what we can see here is this this array is definitely like the final image that it wants to render. I've just interpreted it slightly wrong. So I set a hardware breakpoint in this master array of image data, and it's been written from this rep stosd function. So this is basically kind of like a mem copy. It will repeatedly run this stosd string copy instruction until ECX is 0. So basically the way this works is that you use 3 registers. EDI is the destination register, ESI is the source register, and ECX is the count register. And it will basically copy destination to source until ECX is 0. So just kind of like taking a step back and looking at this function a little bit, we can see that it takes the count from EBX, wherever EBX comes from, and then it shifts it right by 1 and then does a JAE instruction. So what shifting right by 1 does is takes all the bits and moves them 1 to the right, which is the equivalent of dividing it by 2. But what SHR also does is whatever bit pops off the end, because you move them all 1 to the right, goes into the carry register, then JAE will jump if that was 0, or will not jump if it was 1. So what that effectively means is it will divide by 2 and then jump if the previous number wasn't odd. So it does that once and then it does it again. So it's dividing by 2 and then saying, was that number even odd? And then it's dividing by 2 again and saying, was that number even odd? And then it goes into this rep instruction, which is kind of like a mem copy. So what I think this is basically doing is trying to copy blocks of data from one place to the other and then kind of account for the situation where you might not be copying a full block of data. Because after the rep, it decrements the DX register and then jumps back up to the top and starts again. So whatever it's copying blocks of data EDX times. So again, I'm kind of thinking what it's doing is probably copying like rows of image data, and then if that row isn't a multiple of 4, then it's going to kind of account for that. Because you can see in the cases where it doesn't do the jump, it executes this extra code where it copies a byte from EX over to EDI and then increments EDI. So I think that's basically what it's doing, is it's copying like blocks of data whilst it's multiple of 4, and when it hits one that's not a multiple of 4, it will account for the extra bits of data. So I'm going to stop here because I've been looking at this for quite a while and I'm reasonably happy that I found out where the rendering code is. There's obviously much more we could go into given more time, but I'm looking at the clock and not only is it 10 to 11 at night, there's actually this feature for x64 debug where it says time wasted debugging 5 hours and 20 minutes. So I've been staring at this for 5 hours, and not to ruin the illusion of YouTube magic, but this is not the first session where I've sat down to do this. So if this was 5 hours and I've done this several days before, I'm thinking I've probably spent close to 24 hours now reverse engineering this and kind of only just scratched the surface of how the rendering works. But we figured out a fair amount, we've gone down some rabbit holes, we've pulled ourselves back out, and I think we've ultimately ended up kind of roughly where we wanted to be, in line with our original goal, which is how does RollerCoaster Tycoon do its rendering? If you found this interesting, then please leave a comment below on other games you'd like to see me do a deep dive on, because I've had great fun doing this and I'd love to do it again. However, if you'd like to see me deep dive into try and outperform Rust, then check out this next video.